And in the first place, it might sound a bit strange, because this is nuclear spin. I mean, the energy states we're looking at here, these are energies of nuclear spins in the external field. There's no word about electrons. And we are sort of the electronic structure guys, being able to solve the electronic Schrödinger equation. I mean, how does that come in here? Well, this shielding, that is what this essentially is. That's an induced field induced in the electrons. I mean, this is just an extra field, or this together is an extra field induced by this one. This is very much, not only very much, this is exactly the same kind of expression as you have here. You have the external field, and then you have some proportionality constant, which gives you then an induced field. So here, this is an induced field, induced in the electrons by the external magnetic field. And here, there are actually two contributions, although I should have written it with two. There is something which is a direct coupling, really through space. One nuclear spin sees the other nuclear spin, which is called the dipolar or direct spin-spin coupling. But that you only can measure, only sort of survives in solid state when you have fixed geometry. Or when, to be more precise, when the orientation of the molecule with respect to the external field does not change. And that you can do if you have a solid state. But if you have a liquid or gas, the molecules are tumbling and turning around. And this, taking different orientations with respect to the external field, leads to an averaging over all the positions. And if you take the average of that, that's going to be 0. So you can't see that in a gas phase or solution NMR spectrum. And I guess the only ones you really looked at would be solution NMR spectra, and what we normally do. I mean, as far as I know, we don't have a solid state NMR spectrometer. They have one at food in Frederiksberg. So, and then there is this contribution, which survives. And this one, again, is through the electrons. So this is actually called, that's the direct through space, and that's the indirect. And that's sort of, you might remember from your childhood, sort of birthday party game, or maybe your parents told you about that. There was this game that you would sit in a circle, and then the first child whispers something in the ear of the next one, and it goes all the way around, and then it comes eventually back. Well, it comes eventually back to the child, but because what happens here is sort of, you have nuclear spin. That nuclear spin sort of whispers in the ear of the electrons next to that nuclear spin, I have alpha spin. And so the electrons propagate that information over to the other. And so the electrons close to that nucleus tell, look, that one over there, has an alpha spin. So you better, if you want to have low energy, you better be a beta spin now. So that's indirect electron-mediated, you also could call it. Yes?
Why doesn't the averaging cancel that turn out as well? If it's indirect through the spin of the other nuclei?
Because that, what happens here is when you rotate the molecule, the electron spin still keeps its orientation relative to this one. So therefore, never mind how the molecule is oriented in space. That interaction is going to be in the same way. Whereas if you have this one, you can, if I have a big, that's my magnetic field, the external magnetic field pointing in this direction. And now if I have a molecule with two nuclei, both have spin, and if the spin of this one is going upwards, then I guess I get the field lines like this, here down, but here pointing up. So at the position of this nucleus, it's going to point up. Whereas if the same molecule now, and therefore what it does here, it enforces the external field. But if I turn that now around, and I have the molecule lying like this, and I still have, this one has the magnetic, its spin vector pointing up, then I get field lines like this, where here they are pointing up, but here they're pointing down. So now the field from this nucleus A is actually opposing the external field and makes it smaller. So this way, the different orientations cancel the effect of the field from here. Because sometimes it forces the external field and sometimes it reduces. And this doesn't happen here because it's not actually really field lines of through space, but it's really sort of the electrons here orientate itself, and then through Pauli or something, the other electron in the same orbital has a particular orientation because of the first electrons, and that is the same, never mind in which direction the molecule points. Before we can calculate the dipole moment, or express the dipole moment as the derivative of the energy of a molecule in the presence of an electric field. And the same we also can do here. This shielding tensor, or components of that shielding tensor, we can express, we take, so A, and then take again an alpha beta component of that shielding tensor. We can express that as the derivative, the second derivative of the energy with respect to, which one first? Never mind. A component of the magnetic dipole moment of the nucleus A, the alpha component, and then corresponding to the beta component of the external field. And that is, of course, the energy of a molecule in the presence of both of those fields. Two magnetic fields, the external magnetic field and, in a way, the field of that dipole moment. And you can sort of see that here because you have that shielding tensor sandwich between those two. And being an energy contribution. Identically, you can also express that indirect nuclear spin-spin coupling tensor, J, and how did I write it? AB. And then the alpha beta component of that tensor, you can also express as the second derivative then of the energy with respect to, I could do it with respect to the magnetic moments again. Magnetic moment A, the alpha component, magnetic moment of B, the beta component, and then we need some constants, which are the gyromagnetic ratios of the two nuclei, due by H, and the nuclear magnetone, which are the relations. Here, basically this expression mixed together with this one. So we have also for those where there's obviously no classical analog, because spin is not really a classical property. We have an expression of those properties relating to derivatives of the energy in the presence of, and here now, two magnetic moments. And we normally would then talk about that this magnetic moment or the magnetic field here or the electric field before for the dipole moment. These are sort of perturbations of our system. Because now we look at the molecules basically in vacuum, and now we have some external fields or internal fields. I mean, a magnetic moment gives rise to a magnetic field, but that's sort of internal in the molecule. It's not something which I can turn off, on and off outside. Well, I can turn it on and off in a molecule, for example, at least with carbon. If I want to have an extra field, then I replace the carbon 12 by carbon 13, and then I have turned on an extra magnetic field in there.